Sean Baxter has finally written up a proposal to bring borrow checking to C++ to improve safety. What are your views on his proposal, and what approach is CPP2 planning?
So there's a lot there. So first, yes, thank you, Sean, for writing the proposal. That's a big amount of work, and plus to actually progress it through the committee is a huge investment of time that Sean has now started. So thank you, because we can't do anything without a proposal. I think it's interesting and an interesting exploration. There's a lot more detail. I'll point to the CPPCon safety panel that we had, because there was a lot of discussion about this question there, and also in the committee fireside chat, which is already online. There was a little bit there, but we mostly pointed to the safety panel, and that video isn't available yet, but it will be soon. It's really important to explore things. So this work is really important. Sean is brilliant. Like, how many people do you know who've written a C++ compiler on their own, who's not named Bjarne or Sean, basically? So kudos there. At the same time, it's also really important to talk about adoptability. And so it's important to make sure that we find out how to avoid viral annotations, how we have so that you have to annotate the callees before you can use it in a caller, because we know that's a major impediment to adoptability in real world code. We have to make sure that we avoid heavy annotation. So even if it's not in viral, if you have to annotate frequently, then that hinders adoptability in real world code. And so one of the things that I've tried to do in CPP2 is really emphasize compatibility, like things just work out of the box. So example, for safety, for subscript, for bound safety, you can use qt vector, std span, C arrays, and they're just bounds checked when you use them from CPP2 code, because we have the information already in the code, because everybody follows the pattern of for their contiguous containers of making sure std size works. Well, that means I can inject subscript checks at the call site, and I do in CPP front by default. And there's ways to opt out if you're in hot code, of course, but the default should be safety. And so the fact that I can use existing C++ libraries without any change, no annotation, no revving the library, it's not internal in the functions, no ABI issues, they just work when used from CPP2 code and their bounds checked. That's the kind of thing I think is promising. And that is ideal if we can get it. Maybe we can't always get that, but with lifetime, and this is where it comes back to borrow checking. Rust has a great lifetime model, which gives you a borrow checking model, which gives you not just lifetime safety of many kinds, but also thread safety, because you have non-shared exclusive ownership, exclusive mutating ownership, which is great, but it also comes at a cost, right? Even in Rust, where that is native, you write more unsafe code than you do in C# or Java. And that's not a ding, because Rust gives you thread safety. C# and Java give you the ability to write cyclic data structures in safe code without going to unsafe code. So, it's design is a trade-off, and both are safe languages. So I think that it's interesting to see where this goes. But with CPP2, for lifetime, I'm following the model that I still think is very promising, that the C++ core guidelines have already adopted for C++, which is a design I did with the help of many others, that emphasizes lifetime tracking and that already catches many common cases of leaks and dangling. Not all, it's not intended to be formally provable, but many common cases, including changing an iterator, a vector inside a loop and invalidating your iterator. It catches those already without changing std vector, without changing your C++ code. So to the extent that we can do that and maybe merge ideas from those approaches, but really not forget about adoptability and how much can we make work without rewriting your code or updating your compilers or bifurcating the world or annotating a lot, the better off we'll be, because our goal should be to deliver as much benefit as possible to as much code as possible. And as soon as we have to touch the code, that reduces how much positive impact we can have.
That's true. There's a question which I find interesting. In the context of C++ zero-cost abstractions philosophy, how do you see future proposals for making bounds checking in vector or both safe and more efficient?
In that entire sentence, I love the word in, because to me, it's about making bounce checking for stood vector is the goal. In is one way to implement it. Personally, I would prefer not to implement it in stood vector, because let's say that we made a standards change to, and this is something I'm still trying to convince the committee about, right? So not everybody is going to agree with me here. This is my opinion, and I'm going to try to convince people. But if we made vector subscript checking happen by putting the check inside the subscript operator of vector, great, we got that. But we have to then wait for the next release of that standard library. We have to worry about potential ODR issues, although usually we'll just pick the right one. But then if we link in objects that have the checked version and the unchecked version, which one do we take? Comdat folding, all that comes in, but that's manageable. But at the end of the day, the big problem with that is now with that work, we've only fixed vector. Now we need to do span. Now we need to do C arrays. Now we need to do cute vector and list and those kinds of things. That's why I'm very pleased with the way that I'm doing it in CPP front, which is injecting the bounds check at the call site. Because in CPP front today, if you subscript any collection, any span, any ranges view, any cute vector, anything that supports stood size that's contiguous, subscript is just bounds checked. Stood span as is. The GCC one, the Clang one, the libstood C++, libc++, the MS STL one, all of them are bounds checked today in CPP2 without any library change, with no ODR issue, with no waiting for a new library, and they all work. And it doesn't, because if you make the change there at the call site, at the subscript expression, you don't need to go update every library. And so I'm personally very bullish on that. Plus, one other benefit you get is that, let's say you have two call sites in the same file or in two different files. One you want to be bounds checked and one you want to not to be bounds checked because it's in a tight inner loop or something, right? And you've proven the bounds are safe and you've proven the performance matters, so you want to suppress the bounds check. In CPP2, it's easy because bounds checking is on by default and you just opt out in that one file, but they both use the same stood vector. They are one's bounds checked, one isn't. It doesn't matter how you link them together. That's not going to change. One concern I have of doing the bounds check inside vector subscript is now if I'm in that situation, how do I get that same effect? Because the one translation unit has checking, the one does not. I had better have them be using the same stood vector. But are they using the same implementation of subscript operator? If they're both using the subscript notation, that means am I going to now, if I link those together, I can only have ODR, one subscript operator. Do I get the bounds checked one? If so, I'm getting bounds checking in the file that didn't want any. Or do I get the non-bounds checked one? And that way I'm not getting bounds checking in the file that wanted it. So I don't see any way to do it that way without having two APIs that you spell differently, just like we spell subscript and at differently today. And look how useful that is. I view that as a counterexample of usability. It just is. Look at the adoption. It's been there. People have been saying use at for decades. It doesn't happen. And never mind that throwing an exception is probably not what you want to do. So I think the philosophy.
Do you advocate for using at? I mean, it's there, but like.
Yeah, I generally don't, but like it's what we have today. So like if you need, if I'm sure 10 years ago, I wrote something somewhere that said, if you need bounds checking, use at, because that's what you got. That's all there is in the standard. But I think that the right answer is to integrate it with contracts. So what CPP2 does, actually, it integrates it with contracts, but it doesn't do it by declaring a precondition on every subscript function. Like stood vector now has a precondition. What it does instead is the language says every call site of a contiguous container subscript or contiguous view, anything contiguous. It could be a C array, it could be a cute vector, stood span, stood ranges view that's contiguous. Every subscript at the call site is bounds checked, and if you get a violation, the current default behavior is to report a type safety or bounds safety violation using the bounds safety contract group. which if you want to then hook it, you can put in your own, install your own handler for that to integrate with your error reporting system. So all my bounds errors go to my library. That works today. And so I think that's a promising way to do it and still integrate it with contracts. But this comes back to the question that you had earlier about Sean Baxter's borrowing implementation. I think it's great to experiment with. I'm really worried about all the annotations and that I can't use stood vector unchanged and have lifetime safety. I want to use stood vector unchanged and have bounce safety. I've demonstrated a way to do that. It works today, and I didn't have to change anything. And I think that's what's important for adoptability, so people can use it with as least friction as possible, and for impact, that the most possible code gets the benefit of it. And so I think adoptability and impact are very important, pragmatic parts of any design.
So yeah, this actually leads very nice on our next question. Like, this fits really, really nicely together. Are like the C++ safety initiatives arriving too late to fend off the growing adoption of Rust or other safe low-level development languages?
Short answer, no. We're moving ahead nicely. I think it's always great to have competition. So thank you, Rust. And Rust is a nice language in many ways. It has some nice properties, especially for thread safety that nobody else has got. Although I know Swift and others are working on that as well. And things like what Sean's doing to say, hey, how much of this can we affordably get in C++ are great questions to ask. But everybody understands, I hope, that even if C++ was the worst language ever, which it's not, and was like that every second line had a security vulnerability, which is nowhere near where we are. Even if everybody wanted to, there's no way that the C++ code in the world is going to be rewritten in another language in our careers anytime soon. We need to help what's there. There is more new C++ code. I haven't run the numbers, but last time I looked, I would be gobsmacked if this was not true. I expect that there is way more new C++ code being written every year than Rust code. Like just new code, never mind all the code that exists already. I remember with one large ISV I went through just a few years ago, and we measured it several different ways. And just the completely new lines of C++ code in their code base, and they cared about safety and efficiency and those things. Just the new, and they were experimenting with Rust, but just the new lines of code, ignoring modified lines, ignoring third-party libraries that they had put in, just their own new lines of code, was something like 2 million lines of code a year, just at that one project. And so that's obviously a large ISV, but there's lots of code. But to come back to your question, arriving too late, it's interesting. It reminded me immediately of a quote by Bill Gates, and I'm sure other people have said it too, but he once said that people overestimate what can be done in 2 years and underestimate what can be done in 10 years. And that is really true. 2 years ago, people were finally correctly freaking out about, hey, we need to take safety seriously in C++. Already now in draft C++ 26 as of the March meeting, so this news is now 6+ months old already. We decided that there's no more undefined behavior for uninitialized local variables. We did that. We're doing that, and compilers will implement it. So that's and that there's more where that came from, and we're doing it in an adoptable way that doesn't change the meaning of existing code, right? Because by making that behavior undefined and providing an opt-out to get the uninitialized with an attribute, if you want it, you opt into it. By doing that, we've disturbed no existing code. Just recompile it with a C++ 26 compiler, and it's safer. Is exactly the adoptability story we want. We really, really need to make sure we avoid any adoption friction, especially viral annotation or large-scale annotation or alternative standard libraries or needing wrappers. If we have to do that tactically here or there, we'll look at those cases. But adoption and impact, the more we can do without disturbing existing code, the better. And that's a great model. So I'm really glad to see that we did that already in the standards. So thank you for Thomas, JF, and others who had proposals in that area. Thomas has won the day, and all the people who worked on it. More like that, please. I'm very bullish on those improvements.
Yeah, I think actually that's a good approach to make the language safer, not like have a safety header you need to include to use certain features in a safe way.
Yeah, you know, when it comes about this, it comes to this too. It's not just the amount of code. I am not involved in automotive and life safety directly, but I plenty of my friends are, including Robert Secord, who's now the convener of the C Standards Committee, and he's been at MITRE and CERT and security organizations for a long time. Is now at Woven by Toyota. Which is very interested in life safety for cars and driver assisted and various levels of autonomous vehicles and things like that. Safety is super important. He was making the point in a meeting I was in with him just a few weeks ago, and I think I mentioned this at CPPCon as well in our safety panel, that when it comes to life safety, right now, if you want to certify medical equipment, you want to certify a software that runs in a car, you want to run software that's used in aviation, there is this pile of legislatively required features and tests that you must show that you pass in order to qualify to legally use that software in those areas where they could hurt people, and to certify the software meets certain safety. So MITRE is not MITRE. MISRA is an example of that, but also other kinds of tools to certify software. Today, those certifications are for C and C++ code, which means that even though Rust is a safer language on the tin in terms of language guarantees, C and C++ code written with those tools and that pass those certifications and pass those tools is actually today the safe choice, and Rust is the risky choice, and this is not a ding against Rust. Rust will get there. It'll just, in 5 years and 10 years, it'll have those tools too. But it's just like, oh, let's just write it in a safe language. Well, but what other safeties are you giving up? Because there's other kinds of safety than language safety, in this case enforced by tools. And yeah, that's more expensive, et cetera, but it exists. There's this head start and this ecosystem that exists and works. And anytime you bring up a new ecosystem, it costs you and takes time. So it was a new idea to me. And then I totally understood it, but that, 10 years from now, Rust may not have those disadvantages, and that's great, but we have tooling yet to build out. And I see the same thing on the Visual C++ team where I work, where I've been working, and it now has the Rust team as part of our team as well. So I see those folks regularly, and we have a backlog of things to do for Rust as well. All these tools that exist for C++ but not Rust. Where today, if you want to ship a component in Rust, you have to get an exception to the waves running that tool, and so you're taking some risk that it didn't follow that certification, it didn't meet that certification. All this will go away. It's just a matter of time and tooling. It takes a while to catch up with all the ecosystem, and this is what happens when you bring up a new ecosystem. But Rust is a great language. We love it. Don't get me wrong. Just as a practical reality, right now, in 2024, C and C++, yeah, I'm including even C here, which is less safe than C++, are the safe choices for life safety, automotive, aviation, and those kinds of things. Rust will get there too, but it's worth remembering that we run a lot of life safety stuff very well and at high quality in C and C++ today. And we'd love ways to make that cheaper and more affordable and bring more of that safety into the language. So to make it easier.
There's actually a question on that. You mentioned MISRA, etc., but actually there's like the profile plan. So what's the status on profiles for C++? Is it like on the road to 26, 29?
Yeah, they are progressing. I don't know yet that they have a specific landing date, but one of my hopes is I have a profiles paper that I have not written any yet myself, but I have one that I intend to ship next week, proposing very concrete profiles as a starter set. So who knows? Maybe those could make a standard sooner than later. But to me, my understanding is that as we standardize profiles, especially to the extent that they are rules for like that basically essentially define a subset of the language. I don't see any reason why we shouldn't backport those to make them available either in the standard or in practice de facto in implementations when you're using pre C++ 26 or 29 conformance modes. So I should be able to run, like if you, the ones I'm going to propose are basically the C++ core guidelines safety profiles, those like a couple of dozen rules near the end of the document that are specifically about the 4 kinds of safety, about safety, initialization safety, type safety. Most of those rules are about code that's legal as C++ 11. I would love to have those profiles enforceable even when compiling in C++ 11 mode or 14 or 17 or 20. So whether the standard mandates that or just implementations do it de facto, either way, I want that to be available to people. So so they're progressing. I'm going to contribute to trying to make them more concrete and to ship them in a standard, but I also hope they'll be available down level because that's how we make it, again, adoptability and impact. We want to make the impact, as much impact as possible to improve the safety of existing code where we can, or even in older, in code bases that have to compile under older standards modes.
There's a bit of a technical question. If local uninitialized variables are no longer UB, how will they behave? Could you please elaborate a bit on that?
Yeah, so for more detail, see my blog post from March, the Tokyo Trip Report. It's on herbsutter.com. You should be able to find it pretty quickly, Tokyo Trip Report. And that has links to the papers as well. But the short version is, the implementation is required to write to those bits, but we don't say what the value they write is. So they could write like CD, like hex CD, 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 or something like that, or some known value or bit pattern. And the advantage of doing that is that undefined behavior sanitizers can still be able to see, oh, you really didn't initialize your variable. But because it's required to be an implementation well-defined value, it's no longer undefined behavior. You can't get time travel optimizations. You can't get demons flying out your nose as being legal behavior, those kinds of things. The scariness of UB just goes away. You do pay a little for it because you're doing those rights, but if there's a way to opt out where you can ask with an attribute to have the variable really be uninitialized, so you always have a way to opt out and get full performance back, but it's safety by default. And I like the idea of not writing just 0, because if you just jam in the value 0, because that was another proposal, and there's been things like Init that have proposed doing that. If you just jam in the value 0, that solves like 75% of the problems, because maybe that's what the programmer intended and they didn't realize their int was going to be 0. But there's still a large minority, like 20-25% of cases, somewhere in that range, where that's still not a program meaningful value. So A, you've changed one bug to another, so it's still a bug. But B, now you've hidden the problem from your sanitizer, who can, at the runtime sanitizer, because if they don't see the source code and they're just going by the value, they're going, look, oh, look, an int that has a 0 value. Yeah, that looks plausible, and they can no longer easily tell you. Whereas if you jam in a value like hex CD, 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 or something like that, the UB sanitizer can still look at that and say, excuse me, you're using an uninitialized value here. So we're still not defining in the standard what the value is. We're not saying it's 0, because I think that would actually be a worse result, to suddenly backport, to suddenly retroactively change the meaning of your code. That wouldn't be good. But we are making it no longer undefined. The new term is erroneous behavior, where we're giving it a well-defined behavior that is still considered an error. You still wrote a bug. Yeah. You should not have done that. Sorry, it's partly our fault because we let you, but we're gonna make it more diagnosable and not UB. No time travel, no nasal demons, no formatting your hard drive, which is a big improvement, because that really does help also kill some of the exploits, the vulnerability exploits that people were writing with uninitialized variables today. Like, for instance, I give an example in my CPPCon talk. I may have time to give the same example at Meeting C++, where just an array on the stack, you call one function that has a stack array that contains a secret, and then you return from the function, so the stack memory is deallocated the stack frame is deallocated, but the secret is still there in the bits. And then you call another function which has an uninitialized variable, an uninitialized stack buffer that overlays that secret and now can read the secret because it didn't write to it. That will no longer be possible in C++26 because it will write something to those values. So you won't get the secret disclosure, the information disclosure vulnerability. So I love that it's a model where I just recompile my existing code with a C++26 compiler and it's safer. That is exactly what we should be striving for.
Yeah. And I think that's a good thing. And especially like we have tools in the language to, say this is an error and we don't have a value to signal that, then you can use an optional. There's SCD expected to deal with errors and handle them. Recently seen a blog post on how to use exceptions with coroutines, which is something which is not like really how you should do it, or and then on the other hand, we have like a feature which is called contracts. And how's it doing? What are your thoughts on contract-based programming in general?
So first of all, I don't know that we've decided yet whether it will be a TS or it'll be just brought into the standard. I think there's a lot of people working hard on still trying to bring basic contracts into C++26. So we'll have a lot more information at the end of the Wrocław meeting next month as to how that's going. It's currently iffy. There's still I'd say 50-50 as to whether it may make it into C++26. But we'll have that discussion about whether to do that or a TS or something as well. But contract-based programming in general it's a good thing. But the main thing I would love people to know is that when we have this discussion about government agencies recommending using Rust or C# or Go instead of C++ because of safety, contracts has nothing to do with that. It is about safety in the sense that it's about functional safety. It's like making your program have fewer bugs, because the word safety is overloaded. So functional safety, meaning I have fewer bugs and unintended behaviors in my program in general. That's what contracts are about, is about finding bugs and having fewer bugs. But it has nothing to do with the benefits people want to get from a memory safe language. So programming language safety is about giving guarantees. And that's like, oh, you can't get a bounds error because all bounds subscripts are bounds checked. Like that's a guarantee a language can give you. So Rust can give you some of those guarantees. CPP front currently gives you some of those guarantees. Contracts are still good, but you just write them individually on individual lines of code. You opt in to saying what you expect state to be. By definition, writing an annotation here and an annotation here doesn't give you a whole program guarantee, but it's still super useful for finding bugs in your code. So for what's sometimes called functional safety. So it's just important to say, hey, contracts are good. I'm all for them, but they're not part of the answer for the government agencies who say use Rust instead of C++. They're not part of that answer because, just look at it. The other languages that are being recommended instead of C++ don't have contracts either, nearly all of them. In fact, I'm not aware of any currently widely used commercial language that has contracts. So, and let me qualify what I mean by there. No, I don't count Ada. No, I don't count Eiffel. Those are not widely used commercial languages. They're not bad languages. They're just not widely used commercial languages. C# had code contracts. They no longer support that. They backtracked from that. So when you look at the widely used commercial languages, like Rust, I think has a contract proposal. My understanding is it's not pervasive or fully integrated or supported yet. So contracts are good. I think it's realistically, as an industry, we're still figuring them out because no commercial language, no widely used commercial language supports them yet. So we're still figuring out how to make them work. Probably the number one question I get from privately from C++ compiler managers across the industry are, contracts look great, but how do we know that they'll succeed this time when they haven't succeeded the other times we've tried this in the past? Because this is not our first time trying contracts in many languages. And I think that's a valid question, and I've passed that to the subgroup SG21 to please answer that. I have not seen a succinct answer yet, but maybe I missed it, so I'll keep pushing. So do view it as somewhat experimental in the sense that we hope to succeed where others have not yet, but I think still useful. But it's quite separate from the memory safety problem that has nothing to do with programming language safety guarantees. It has everything to do with debugging my code, finding bugs tactically, and being able to get functional safety of the kind where, okay, I've reduced the bugs in my code, but that's not the same as programming language memory safety, which is about whole program, whole language guarantees.